So we have seen the isotopes, different positron emission isotopes which are used yesterday. So we will see how these isotopes are produced. We have seen how the cyclotron and how the irradiation material is kept in the accelerated particle beam ka path, and how the material is made into positron emission radioisotope. So we will see into details each of these isotopes, how it is produced. So for oxygen 15 production, the basic chemical reaction that take place is nitrogen is bombarded with deuteron and oxygen 15 is made. So deuteron, the nitrogen gas is placed in the cyclotron and bombarded with deuteron particles to produce oxygen 8, oxygen 15 and 1 neutron. So the irradiation time is about 6 minutes and about 12,000 millicurie of oxygen 15 can be produced in one cycle of the cyclotron run, and half-life of this isotope is 2.05 minutes. And carbon 11, so we have the target material which is nitrogen gas, which is bombarded with a proton. So nitrogen bombarded with proton, we get 6 carbon 11 and 1 alpha particle, 2 He4 2 plus. So here irradiation time is about 30 minutes and we could have around 3000 millicurie of activity of carbon 11 in one cycle of cyclotron run, and half-life of carbon 11 is 20 minutes, 20.35 minutes. And you can see here for oxygen 15, the different traces are the pure oxygen 15 and H2O with oxygen 15, water with oxygen 15, CO2 and CO. So it can be in the form of oxygen gas, it can be in the form of water, it can be in the form of carbon monoxide or carbon dioxide, the traces, where the normal oxygen is replaced with the radioactive positron emission radioisotope of oxygen, which is 15. And here with C11, the traces are CO2, CO and HCl. Where the normal carbon atom is replaced with carbon 11 atom. And F18 is produced by bombarding oxygen gas with proton particle. So oxygen is bombarded with proton, we get 9 fluorine 18 and 1 neutron. So the target material which is normally used is heavy oxygen in the form of enriched water. So here the irradiation time is about 60 minutes, and the yield of F18 production is low even after a long duration of irradiation time, and half-life is 109 minutes, 109.74 minutes. So this is the most commonly used positron emission radio tracer which is used in the routine clinical practice. So nuclear reaction involving oxygen, proton, neutron, we get F18, and target medium is heavy water, and beam energy 16.5 MeV protons. And water container metallic silver, and target volume is about 0.8 ml. And fill volume is 1.1 ml, and target pressure is 30 bar or 3 megapascal, and target foils hover 25 and 50 micrometer. foil cooling by recirculating the helium gas, and target cooling is by deionized water in the cyclotron. So here we have uh, neon gas proton alpha reaction, we get F18, where with neon gas plus 0.3% F2 is irradiated with 16.5 MeV protons, and target chamber is metallic aluminum, and target volume is about 60 ml, and target length is 130 mm. Target fill pressure 10 bar. Target foils have 25 micrometer of two numbers, and foil cooling by recirculating helium, and target cooling is by deionized water. And in carbon 11 production, we use nitrogen 14, which undergoes proton alpha reaction to produce C11. So the nitrogen gas is bombarded with 16.5 MeV protons, and the target length is 250 mm, target volume is 78 ml, target fill pressure 10 bar, and target cooling is by deionized water. Target foils have 25 micrometer, two numbers, and foil cooling is by recirculating helium. And for the N13 production, the oxygen 16 undergoes P alpha reaction to produce N13. So the distilled water is the target medium, which is irradiated by 16.5 MeV protons in 0.8 ml, and at the target pressure of 6 bar, and target cooling is by deionized water, and target foils are titanium or HAVA 25 micrometer, and foil cooling is by recirculating helium. And oxygen 15 is produced by radiating nitrogen gas with 8.4 MeV deuterons. So N14 deuteron-neutron reaction give rise to oxygen 15. This equation you need to remember, and the half-life you need to remember. So other things, if you can remember, that will be good. And beam energy of the interacting deuterons are 8.4 MeV, and target chamber is aluminium. Target length is 110 mm, target volume is 35 ml, target fill pressure is 10 bar, target cooling is by deionized water, and target foils have 25 micrometer, two numbers, and foil cooling is by recirculating helium. So this is the picture of a hot cell where FDG is produced. So in the cyclotron, the FDG is produced and we get it out at the other side of the cyclotron. And we can have multiple runs per day. We have seen that in a cyclotron, by one run, the target yield is somewhere around 300 millicurie for F18 and 3000 millicurie for carbon 11 and 1200 millicurie for oxygen 15. So another thing is 1200 and 3000 will look like a huge number of huge amount of radioactivity in terms of if we look at it, but then the half-life is too small. So if we have a patient for their whole body scan, if we have to inject around 15 millicurie, so then for that 15 to 30 millicurie, so for that you will need to, if you are in, depends on the from the site of production to the place of use, so you need to have much more amount of activity in case the half-life is less. So this 3000 millicurie is not a huge amount when it is of carbon 11 with half-life of 20 minutes or oxygen 15 with 2 minutes half-life. So in 2 minutes, this 1200 millicurie will become 600 millicurie. So that is how it is. So So a cyclotron is capable of running multiple cycles of production in order to have large amount of radioactivity production of PET isotopes. So important considerations at the time of installation are space requirement, wall thickness. So this positron emission isotopes have the gamma radiations are of 511 keV. Positrons are nothing but electrons with positive charge. So they recombine with electrons and then produce this 511 keV photons. So these photons are we need to have the shielding requirements depending on the energy. So usually in X-ray, CT and all, we are using maximum up to 140, 150 keV. So here we have 511 keV. So it's like almost 4.5 times the energy of the usual X-ray photons. So correspondingly, we have to consider increased wall thicknesses for safe handling and radiation protection practices, and shielding configuration, safety interlocks, ventilation requirement, targetry system, and vacuum system, extraction system, power consumption. All these things we needs to consider before the installation of the cyclotron. And the subsystems include power supplies, water cooling system, targets, precursor chemistry, gas distribution, automated chemistry, shielding, radiation interlock systems, and radionuclide transport system. So there are two types of target system which are used. So it can be either a liquid target or gas target, as we have already seen. And prior to the production, the following steps are to be followed. Preconditioning of target by irradiating oxygen 16 distilled water at 25 microampere for 10 to 15 minutes. The activity from the target is filtered before delivery to the synthetic synthesis module. And quality of enriched water is very important factor for the long life of target and target yield. And power density, watt per centimeter square, is an important parameter of target designing, which depends on beam size. It is required that the power density should be distributed throughout the target. The cooling system generally consists of primary chiller, secondary cooling system, and heat exchanger. The cooling system is a closed system which cools the target and cyclotron subsystem, especially magnet, RF, etc. The heat generation during irradiation can be controlled by double foil technique, that is water cooling on backside of the Havar foil and re-cooling on entrance foil in closed circuit using the helium gas. And the vacuum system, where the accelerator chamber has to be maintained under high vacuum in order to avoid collision of accelerated ions, protons with any other gas molecules. So you know protons are nothing but hydrogen gas removed of the electron. So in standby mode, the vacuum always maintains at least 10 raised to minus 7 millibar, and during irradiation it is to be 1.2 into 10 raised to minus 5. The vacuum is maintained by rotatory and diffusion pumps, and extraction system consists of two beam extractors that intercept the accelerated ion beam with a carbon foil. The production yield at the end of bombardment depends upon the beam current and time of irradiation. In order to avoid the water and tear of the target, wear and tear of the target, it is better to operate at low current and for more time. And RF system supplies an alternating high voltage potential to the Ds at a frequency of about 27.2 megahertz. Magnetic system provides the bending force that confines the beam to the circular orbit centered between the upper and lower magnet poles. of magnetic field strength 1.8 Tesla. So a brief history of PET. So the positron was discovered by David Anderson, Carl David Anderson in 1932. In the 1950s, first applications of positron isotopes in medicine by Wren in 1951 and Brunel in 1953. And in the 1960s, projection imaging first attempts at tomography. Anger in 1963 developed the Anger camera and BNL ring. And in 1970s, filtered back projection makes tomography feasible. Helps Hoffman and Terprogasian develop PET-3. So you can correlate it with the CT, MR imaging and the image reconstruction and all the computer technology which came into picture. Early 1980s, BGO detectors improve resolution, block detectors make extended AFOV system practical, and small companies making scanners like CTA, Scandronics, PET, etc. And in late 1980s and early 1990s, 3D improves sensitivity, and large companies involved like Siemens and GE, actually these large companies bought the CTA and SCX. And in the mid 90s, clinical oncology applications emerges, drive for lower cost PET designs by pen PET or Quest, ART, PET on NM equipment, etc. So from a head scanner, we have come a long way by having advanced detector materials, detector configurations, and multiple radioisotopes and radiopharmaceuticals. So this is similar to nuclear medicine, where we have functional information based on the biochemical function in the body. Uses a chemical or a pharmaceutical that is labeled with a radioactive tracer, and the radioactive tracer emits penetrating radiation. The penetrating radiation can be detected outside the body. Like in nuclear medicine, we have technetium-99m or other radiopharmaceuticals which emits a gamma ray. In positron emission tomography, the radiopharmaceuticals emits a positron, which in turn combines with an electron and give rise to two 511 keV photons. And these penetrating radiation can be detected outside the body. And most PET studies use the radiopharmaceutical FDG, fluorodeoxyglucose, and where the fluorine is replaced with the F18. And carbon, oxygen, nitrogen are also used, as we have seen. More radioisotopes may be used in the future. Now we have serious problems with the half-life of these positron emission isotopes. So what does PET show that CT, MRI, X-ray, ultrasound and nuclear medicine don't? So CT, MR, X-ray, ultrasound shows anatomy, and nuclear medicine shows function, and whereas PET gives us the information about metabolic function inside the body. So people are not made of iodine or technetium, indium, gallium, etc. So they are made of carbon, oxygen, nitrogen, hydrogen, etc. If we look for radioactive isotopes of these natural biological atoms, we find positron emitters, which are useful in metabolic imaging of the human body. So this is why the old radiology departments became nuclear medicine department, separate nuclear medicine department. Then the nuclear medicine department became nuclear medicine and molecular imaging department. So this kind of subdivision or categorization happens because of this clinical applications of these imaging modalities. So why is it important? Because FDG is a wonderful radiopharmaceutical. We know the metabolic activity, what happens in our body is glucose gets metabolized. So you can see the similarity. So glucose is C6H12O6, where one oxygen is removed and replaced with the radioactive fluorine. So FDG is fluorodeoxyglucose. One oxygen out of the O6 is removed and replaced with a fluorine atom. So glucose is metabolized in every cell to produce energy. Although all cells consumes glucose, the more active the cell is, the more glucose it uses. And body do not understand or differentiate between glucose and FDG. So we can make use of this in order to get functional information about the metabolic activity, metabolic rate inside each of the cells. So it is similar to glucose, as we have seen. It is made by removing one of the oxygen atoms and replacing it with a fluorine. And when the FDG is metabolized, the carbon dioxide and water diffuses from the cell, but the fluorine is trapped in the cell. So therefore, the uptake of fluorine in a cell is directly related to the metabolic activity of the cell. So more active the cell is, or more metabolism happens in a particular cell, the more will be the amount of fluorine getting trapped. So fluorine is F18, which emits positron. So this fluorine 18 FDG is injected into the patient. We know that in nuclear medicine we have different methods of introducing the radiopharmaceutical into the patient. It can be injected, it can be ingested, it can be inhaled. So here in we are injecting the FDG into the patient, and then what happens is shown. So the hexakinase and glucose 6 phosphatase FDG and the FDG 6 phosphoglucolactone and the HMP shunt take place. And as we know, the more active the cell regeneration, the more metabolism takes place and more amount of glucose transfer, glucose metabolism takes place, and more amount of F18 will be trapped in those cells. So this we will be able to observe in the PET scan images. So we have seen this. This is a compilation of the particle accelerated, the target which is irradiated, and the positron emitter we are getting, and the radioactive material. So when proton is bombarded with enriched nitrogen, we get oxygen 15. Again, 16 oxygen water is bombarded with proton to produce nitrogen 13 and alpha particles, and enriched water 18 oxygen water is bombarded with proton to get fluorine and neutron, and nitrogen gas 14 and nitrogen gas is bombarded with neutron to produce oxygen 15 and neutron, and neon gas is bombarded with neutron to produce fluorine 18. So this is another table. This is most of what you need to remember regarding PET isotopes and tracers. So we have seen the isotopes and their characteristics, the production, nuclear reaction, target media, half-life, and the chemical form we have seen. So where it is used. So the C11 carbon dioxide is used for metabolic heart function evaluation, and carbon monoxide C11 is used for blood volume studies, and HCN carbon 11 is used for tissue glucose metabolic studies, and oxygen 15 is used for and 15 oxygen is used for oxygen metabolism. 15 carbon monoxide is used for blood volume studies again. Carbon 15 carbon dioxide is used for blood flow, and oxygen 15 water is again used for blood flow studies. And fluorine isotopes and fluorine tracers. Fluorine 18 is the most commonly used for skeletal evaluation, and F18, FDG could be used for glucose metabolism, stroke, dementia, epilepsy, tumors, Alzheimer's, and many more of the non-carcinoma dysfunctions in the body. And F18 is again used for brain studies also. So another problem with fluorine PET since this is based on the metabolism and metabolic rate, the normal distribution of the normal metabolic distribution inside the body, the brain will be shown very highly hot in the image. So that is a challenge for brain studies. So that is done using this specific isotopics, modified specific isotopic study. So coming to the tomography, the machine where how we are utilizing this. So I was telling you this isotope will produce a positron which is beta plus, so that travels a short distance and annihilates with an electron. So the annihilation process produces two photons, and conserves the energy. So energy to each photon is 511 keV. So what is this 511 keV? So we have a positron and an electron. So the rest mass energy of an electron is 511 keV. So the mass is converted into energy here in this transition. So energy of each photon is 511 keV, and momentum, so photons are back to back. So you can see each of these 511 keVs are emitted out once the positron gets combined with a electron and it annihilates to produce 511 keV photons. So from the point where the positron emission took place, it travels around 1 to 3 mm in the tissue. In that period of time, it gets combined with the electron and gets annihilated. So this simultaneous detection of these two 511 photons as an event was along the line between detector pair. So both of these 511 keV photon needs to be detected within a window frame so that it is identified as a single annihilation event. So this photon is detected by, say, this detector, part of the detector, this one, and the other photon is detected by the detector which is 180 degree apart, and this needs to be detected in a specific window time for it to be considered as an annihilation event and contribute to the image formation. So here again you can see a little bit more of how the annihilation detection is taking place. Here you can see this gamma is traveling a shorter distance. This is where the annihilation event took place. So this photon, the one which is coming down, is traveling a shorter distance, while this photon is traveling a longer distance to register at the detector. So when both of these are detected by these two, specifically these two, the detector, say this is detector 5, so then the detector which is 180 degree away apart from the detector, if those two detectors are identifying one photon, then only that will be considered as a coincidence. So this is how the coincidence detection takes place. We have two channels and the summed channel. If there is a detection in the channel 1 and there is a detection in the channel 2 at the same time, then we will have a coincidence event. You can see the bigger peak over here. This gets added. So here you can see there was an incident. There was a photon which is detected. So each detector pair is connected with this channel 1 and channel 2 as channel 1 and channel 2. So the detector pair needs to detect two photons in the same time frame, then only it will be considered as a coincident event, giving rise to the resultant. So the AND function, AND gate, you can see that is what is utilized here in the multi-channel analyzer. So the events occurring anywhere on the line between detectors contribute coincidence counts to the detector pair. Recorded counts are proportional to line integral of activity between the detectors. So how the projection data collection is done? So from the detector, there is a the annihilation and detection at these two, which are 180 degree apart, and the photomultiplier tube detects the light photon, and then the processing electronics does the coincidence processing, and the coincidence processor give its output to the data sorting and histogram production, and then from that the image reconstruction is done using the computers, using the similar or same kind of algorithms which we used in So this is what is happening in PET. So once the radio tracer is injected into the patient, radioactivity goes all over the place, all over the body by the blood circulation, and then wherever more radioactive, wherever more metabolism is taking place, more of the fluorine will get trapped over there, and then the more of gamma rays will be emitting out of there. But all over the body, some annihilations will be taking place, and they will be giving rise to 511 keV photons. So these photons, since they go 180-degree apart or exactly opposite directions, so we utilize the ring detector gantry formation for the detector pair to identify these two events. So it is pictorially represented over here. So if two detectors are placed so that each detector detects one of the pair of gamma. And it is more important and most important that the signals at the two detectors occur at the same time window of time. So the gamma rays travel at the speed of light, and if the difference in path length is 30 centimeter, they will arrive 1 nanosecond apart. So speed of light is 3 into 10 raised to 10 centimeter per second. So the more detectors present around the patient, the more pairs of gamma rays will be detected. The only way to know which so that is why I was stressing on the word the timing window. So any two gamma rays that arrive within 12 nanoseconds are assumed to come from the same position. So all the projection data is collected. So all the annihilation events which is taking place and which are captured by the and these detector pairs are part of the detector ring, which is part of the gantry of the PET scanner. So here you can see different color lines. The projection data is collected for each pair of rings as well as within each ring. So there can be random detections, there can be attenuation, there can be scatter, and there can be dead time. So we will see the multiple events taking place and getting detected. You can see here with different lines. So all coincidence events are counted, which includes random and scatter. So coincidence events which are left after randoms and scatter have been subtracted. Even loss to attenuation or sensitivity are not replaced when measuring counting rates. So here you can see so say 1, the white line, the annihilation takes place here. The photons are detected on the opposite detectors. And 2, the annihilation takes place here. It is getting detected in the same this thing. So, and the event 3, the annihilation which took place here, you can see it is getting scattered. One of the photon is getting scattered over here and it is not reaching the detector pair. The other event is getting detected over the detector. And the event 4, so one photon is getting detected on this detector, but the other photon which was supposed to be going like this, so that is getting scattered on its path and getting detected on this line. So here you can see the position. There can be a positional inaccuracy here with respect to this thing. The annihilation actually took place here, but the detector is considering it as it took place on the direct line over here. So this could happen with this. And you can see 5A and B. So there are two annihilation events. So, and each detector is detecting one of that. So this also will be counted as a incidence, but then coincidence, but then it is happened somewhere else. It is not a true coincidence events. So you can see one, the white line is a true coincident event, and detector two, true event lost to sensitivity or dead time, because you can see here the detector is the photon has to travel a shorter distance, and here it has to travel longer distance. And three, you can see the true event lost to photon attenuation. This got scattered and went off. And scattered coincidence event is the fourth one. You can see here the one photon gets scattered on its path and getting detected as a coincident event. So this is getting counted, but it shouldn't be counted. And this is the fifth one is two scatter are getting falling on the detector, and it is getting counted, but then it shouldn't be counted as a real event. So reconstruction is pulling all of the data together to form useful image. So 3D reconstruction happens in the 3 dimensions. All the across the detector, across the patient, all the incidences took place. All those things are time and space matched to form the 3D reconstruction. So this is a projection generated from a single central point source. So here you can see 3 projections, 3 signals are formed from the central point source. So this is ramp and Hanning filter or bow tie filter, you remember in CT. So it is similar to that. So the data with the diamond is the ramp filter, and with the Hanning filter is with the square. And the back projection of a point source with finite number of back projection angles forms a star artifact. Here you can see a star forms the overlap between multiple beams. And if you have more number of this thing, there will be a bigger star, but then you can have a difference in the intensity of beam with respect to the central intensity and the surrounding intensity. So these are called star artifacts. So now we have understood there is this distance traversed and the total distance between the two detectors. So you don't need to remember all these equations. So the correction method for gamma attenuation in tissue is done by these probability of photon reaching detector 1 and probability of photon reaching detector 2, and the probabilities are independent of each other, and both photons must reach the detectors for a coincidence to be recorded, and the probability of a coincidence is the product of P1 and P2. So here you can see without attenuation correction and with attenuation correction, the difference in the image quality. So the other useful terms related to performance specifications of PET: resolution, sensitivity, count rate performance, and scatter fraction. Performance measurements, spatial resolution. You know what is spatial resolution? It is the same here also. So how big does a point source appear to be? And the smallest thing which we can imagine. So spatial resolution is measured with a very hot point source and with no background activity. So how well we can resolute between with a point source? How small a source can be identified clearly in the image? That is the measure of the spatial resolution. How the quality assurance test is done, that varies from CT scan to MRI to PET, but the concept spatial resolution is the same. And detector design, now that we know how a PET scanner works and what is important for good performance, let's see a good scanner and what all are required and what are our objectives or goals to be achieved from the machine. So we need high spatial resolution. For that, we need small detector elements, high photo fraction, and hence the high sensitivity. We need high stopping power of the element, and low scatter fraction. We need good energy resolution, and low randoms. We need good timing resolution, low dead time. Uh, we need fast event handling, small channel size, limited multiplexing, and low cost. All these are not involved with all these should be able to be achieved at a lower cost, at whatever minimum cost we can achieve it. And the crystal properties for the detector, we need high density, so overall detection efficiency is proportional to the product of the detection efficiencies, and high effective atomic number, high photopeak fraction. Photopeak versus Compton allows high discriminator setting for scatter rejection. So fast decay time, it allows the primary speed of the detector has a big effect on the count rate. And other factors, light output, wavelength, and the index of refraction are other properties that are important. So within the crystal also we can have refractions taking place and adding to the non-realistic events which are not real but detected as coincidence events. And the crystals also, if the lower the cost, the better. So there are different detector materials which are commonly used. So, and their specific characteristics are tabulated over here. The sodium iodide thallium crystal was used in first systems and still effective. But BGO is dominant in scanners today. BGO is dominant in PET scanners today. And sodium iodide thallium is still useful, used in gamma cameras, SPECT cameras basically. And most of the PET scanners are replaced with BGO crystals based on the mu Z despite low light output. Now LSO is also intriguing and available in few of the systems. So the characteristics and how it is, the comparison is shown over here. the stopping power, light related characteristics and crystal related characteristics. And here again are the properties of the scintillator material which are used in the PET scanners. So the effective atomic number, linear attenuation coefficient, index of refraction, light yield, peak wavelength, decay constant, fragile, hygroscopic. And here are some of the detector assemblies which are commonly utilized to overcome some of the crystal characteristics or crystal deficiencies. So we had one-to-one coupling, one crystal, one photomultiplier tube. So where the excellent lifetime characteristics but expensive and limited in size to smallest available photomultiplier tube. So this is approximately 1 centimeter square. And Anger hangara, where light from scintillator is distributed among several photomultiplier tubes, measured in distribution determines location, but poor lifetime, but can have good resolution with enough light output. So sodium iodide thallium crystals are also used in still used in Anger cameras, where single crystal, multiple photomultiplier tube. So you can see that the crystal size increases and correspondingly we will have the problems associated with the life of the machine, but the light output resolution will be better with the use of multiple photomultiplier tubes. And the block detector, where individual crystals and pipe light tube detectors, more complex but required with low light output. Example is where BGO crystals are utilized. The pictures are self-explanatory over here. So these are some pictures of the real-time photographs of so here you can see the number of crystals are 36 of the size 4 into 8.5 into 30, and PMTs, dual PMTs are utilized for a block area of 2.4 into 5 centimeters square. So here again the detectors, crystals and the photomultiplier tube. You can see the photomultiplier tube. So the sides of the photomultiplier tubes are hexagonal in shape, so that proper stacking of the photomultiplier tube could be done in the area, so that no light photon emitted by the scintillating crystal is lost. So there are different light coding for the block detectors. So cuts or different where different lengths are utilized, and surface treatment where rough surfaces are polished, and surface treatment with variable painting. So you can see the different paintings are done for getting it equal. So how the block detector detects the light photons from the crystals, and how the each of the total energy centroid of light distribution is detected and electronically computed for the utilization. This is another picture of detector module. crystals are there, photomultiplier tubes are there, electronic circuitry is there. So this is the architecture of PET detector. So if in one block 2 PMTs, 36 crystals, and one cassette 6 block 12 PMTs, so that results into 216 crystals, and 56 cassette 336 block and 672 PMTs, resulting in 12,096 crystals, and 18 rings have 12,096 crystals, so 672 crystal rings will be there. So you can assume this is the modification done to the detector system to improve and account for the improve the characteristics which are favorable to good imaging, and minimize the effects of the characteristics which are not favorable to good imaging. So lead shielding septa are there, which are not really collimators but something like collimators. Here in the PET detector system, we do not use the collimating system. The collimation is done by the annihilation detection, coincidence detection, and the windowing of time and space. So this is a picture of the gantry ring. So he is the inventor of the cyclotron system who have devised the Ds where the particles can be, the direction of the particle can be bent using magnetic field, and the acceleration can be achieved within a finite distance. So, in his words, scientific achievement is rooted in the past, is cultivated by contemporaries, and flourishes only in a favorable environment. No individual is alone responsible for a single stepping stone along the path of the progress. So, we'll stop here for today. Thank you.